Hi, I'm very happy to welcome you to this talk about blind and channel-agnostic equalization using adversarial networks. My name is Vincent Lauinger. I'm from the Karlsruhe Institute of Technology in Germany, and this was a joint work together with Manuel Hoffmann and Laurent Schmal, as well as Jonas Ney and Norbert Behn from the Technical University of Kaiserslautern. So the autonomous driving, Internet of Things, the Industry 4.0, etc., leads to manifold channels and transmission parameters and so on. So preferred would be a one-system-fits-all solution. And hence, there's a great demand for flexible and blind equalizers, where increasing the flexibility enables autonomous network automation, which is crucial for the digital transformation, and the saving of the data rate due to the blindness can increase the FEC overhead or net data throughput. So ideally, what we want to have is a topology and model independent, a channel agnostic transceiver. However, state-of-the-art blind equalizers or blind algorithms are usually the channel dependent. So the loss function assumes certain characteristics, for instance, a linear channel, or it's topology dependent. So the equalizer block have to have a certain structure. So let's have a look at a very general system model where we transmit X, some data X, through an unknown channel, and we receive Y, and the receiver then tries to recover X. So X hat, the output of the receiver, should be equal to X. That's our goal, and this means that also the distribution has to be the same. So P of X hat has to be equal to P of X. And this, in fact, is the goal of generative networks. But be aware that X contains information, and this information has to be preserved. So this corresponds to that the conditional of the receiver, so the P of Y given X hat, has to be equal to the channel likelihood, so to the P of Y given X. But as I said earlier, we don't know this channel, so we have to ensure this by the training algorithm or by appropriate receiver topology. And in between all this generative networks, in the recent years, the generative adversarial networks had a great success in different fields, for instance, in generating new samples from reference data. So this person actually does not exist. So this is generated, this is a photograph generated by a gun. And it also has been used for rendering images to art or vice versa. So here's a painting of Monet and it transferred it to a corresponding photograph. Or there's a photograph and it transferred it to a potential picture of or potential painting of Monet. And in communications, there also have been a couple of proposals, but there's one where they tried to learn a decoder by unsupervised training via adversarial networks, and this kind of has the same target or the same tries to do the same as what we do. So this, in fact, motivated us as well to use adversarial networks to train a blind and channel agnostic equalizer. So what is a GAN? GAN consists of two main building blocks, a generator G and a discriminator D, which are parametric functions and usually implemented by neural networks. And the generator gets Y as input, which is usually some noise, and outputs Z. And the discriminator tries to discriminate between the generated samples Z and some reference samples X prime. And so these two, the generator at the same time tries to fool these. So these two networks, they are trained at the same time, but in an adversarial manner. So it's, you should say it's a min-max game. And this approach was proposed by Goodfellow, and he also showed that the global optimum of the scheme is at P of Z being equal to P of X. So the distribution of the generated samples being equal to the distribution of the reference samples. And that's actually our goal. So how can we use this structure for our purpose? And the key point is that instead of inputting the some noise to the generator, we input the received samples. So Y is the output of the channel, and in fact contains information. And then the generator basically becomes the equalizer. So here, this top line corresponds to a typical transmission system. And only these two parts down here, they are additional for this GAN training. So the sampler now samples, so creates reference samples, which are drawn from the same distribution as the transmitted symbols, but that's not the transmitted symbol. So here we are blind, as I said already, which means that it draws some random samples from the same distribution, but random samples. And the discriminator then estimates some divergence, which enables the update of the equalizer. So it kind of learns the loss function, if you want to say it like this. So how did we implement this? For the generator, we used the convolution network with 2 hidden layers. And this is quite a large structure for our purpose. So we also tried a very simple, small one. Here we used only one layer, on one convolution layer, which in fact corresponds to a simple FIR filter. And thus it corresponds to a linear equalizer. And for the discriminator, we used a fully connected neural network with one hidden layer. And some training details. We implemented the NS GAN approach, the non-saturating GAN, which was already proposed in the original GAN paper. And we also used historical rate averaging. And for the evaluation, we chose quite a general transmission model with pulse shaping, and then some linear distortion modeled by impulse response, and some function FRX, which where we can model some nonlinear behavior, and then we superimpose AWGN. And the first channel we look at is an AWGN channel with memory. So this is a linear channel. So FRX is identity. And we use the Pruakis B channel impulse response, which is actually already quite demanding, quite a challenge. And for the second channel we look at is an IMDD channel. This here we consider the linear channel distortions caused by chromatic dispersion, and here we use the standard values of a single mode fiber, and this is a nonlinear channel because the square law detection introduced some nonlinearity, so some squaring, and this is modeled by the FRX function. And we also did some averaging, so all the results we now show, they are averaged. And in fact, we estimate the SAR after each iteration over 10,000 symbols. And then over all the SAR estimates, we perform a moving averaging with a filter length of 10, and then choose the minimum. So the displayed results are averaged over 10 times 10,000 symbols. And here we see the results for BPSK through the AWGN channel, the symbol error rate over the SNR, and we see that the proposed GAN approach basically converges towards the supervised CNN, so it follows the same track. And the supervised CNN, it uses the same generator block, so the same equalizer, the CNN, but trains it in a supervised way. So this is a non-blind reference. And if we look at the linear equalizer, we see that it in fact outperforms the other linear equalizer references, where we have an LMS and again the supervised training. So that's also both supervised and non-blind references. So the GAN here outperforms the non-blind references. And then we transmit PAM2 through the IMDD channel. We see here the symbol error rate over the symbol rate. So the symbol rate, in this case, it corresponds to the chromatic dispersion. And we see that the GAN is not quite converging to the supervised CNN, but it outperforms the supervised Volterra. So here we use the Volterra structure and trained in also supervised, so also non-blind, and the GAN can outperform this reference. And the dashed lines now, they show the minimum. So far we looked at the mean SER, but now the dashed lines correspond to really the lowest SER which has been reached. And we see for the GAN higher variance, and in fact we see that it reaches a lower SER than the supervised CNN. So yeah, if we now look at the linear equalizers, we see that they perform quite similarly, and they can't quite cope with the with this channel in the same way as the CNNs. So far, we only looked at binary signals, but here we transmit a multi-level signal, a multi-level format, so PAM4 through the IMDD channel, and now the linear equalizers did not converge anymore. But we also see that the GAN is now converging towards the, well, yeah, it's performing similar to the CNN, to the supervised CNN, or even outperforms it here at this working point. So, and again, outperforms also the Volterra equalizer. And if we look at the minimum, we see that the variance now of the GAN is rather small. So let's have a closer look at the convergence behavior of this algorithm. And therefore, we display the simple error rate over the training iterations. And we see 3 runs, 2 which converged properly and 1 which didn't converge properly. And now, first, I show the histogram of the equalizer output of the well-converged runs. And we see that it takes some time, it moves a bit around, but then it finds track and it converts properly, and also it separates the symbols properly. And if we now look at the non-converged run, we see that it also has some gasp in the beginning, but then it somehow shuffles the symbols around and does not converge properly anymore. So this brings us to the conclusion of this talk, and we proposed a novel approach for blind and channel-agnostic equalization. We proved this concept's feasibility. We demonstrated the approach's flexibility and potential to converge towards the performance of non-blind reference equalizers. And also, we showed that the algorithm is sometimes not converging properly. So we would say that this proposed equalizer is highly relevant for the future research, and it's also the next step towards integrating deep learning into communication systems. So as an outlook, I would give the improving of the training stability, some topology optimization could be possible, and also we want to highlight that this is an adaptive approach. So an analysis in time-varying channels might be worth as well. Then thank you very much for your attention and your interest. If you have any questions or any remarks, send me a mail or contact me in another way. And yeah, thank you and have a nice day.